So thanks for inviting me here. The work I'm going to present today has been done mainly by the two guys that you see over there, Tom and Alessandro. So just to start with, I would really like to thank them for everything they've done. As you've been told, my name is Vincent. I work at Meta. I'm part of the PyTorch team. Specifically, I'm like the person of contact for reinforcement learning within PyTorch. So if you're doing RL and you have any questions, just feel free to drop me an email or ask me during the conference or whatever. Always happy to help. Right, so today we're going to talk about fine-tuning generative models through what we call RLHF, which stands for reinforcement learning from human feedback. So if you train a generative model, so let's stick to large language models for easy of use, but it could be anything, image generation or whatever. So let's say you train that on static data, something like Reddit or Wikipedia or another corpus. The problem is that your model will quickly become misaligned. And what it means is that if you have a very simple task like a text with missing words, the model is very good at filling these missing words. But if you start interacting with the model and trying to make a conversation with that model, you're going to have a hard time having some quality output, okay? So what it means is that the model has a very poor out-of-the-distribution performance. And what you want is for that model actually to do much better than that. So what you want is that for the model to be helpful, honest, and harmless. And when trained on the static data, none of these models is really able to do that. And the problem is that having a conversation of a high quality is very hard to model through a simple loss function. It's something that is mathematically hard to formulate. So the solution that people came with is to use human feedback, something like an accept or reject, or a ranking based on the answers that the model is giving you to tell the model when it's wrong, okay? And that is when reinforcement learning comes into play. So what is reinforcement learning? So here I have two graphs, one that is more generic about reinforcement learning on the top left, and on the bottom left you have the version that is specifically for fine-tuning of large language models. So for those who don't know, reinforcement learning is usually framed in the following way. You have an environment, okay? So the environment in this case, it's the user in front of ChatGPT, interacting with ChatGPT. And you have an agent. So the agent is something like the neural network, the model, something that basically takes the observation from the environment, so from the user, and out of that outputs an action, okay? And in reinforcement learning, we frame that problem as for the agent in the environment to try to maximize a certain notion of reward. So the reward here is going to be just the agent, so you as a user, for instance, telling the model whether it's doing good or bad, okay? So it's quite easy, actually, because if you formulate it that way, you're just talking with ChatGPT, you're looking at the answers it's giving, and every time the answer looks good, you say, okay, that looks good, and every time it looks bad, you say, that looks bad. You can do something a little bit more fine if you want. You can also rank the answers, so you can ask the same question multiple times, and then basically tell the model, okay, this was the best answer, this was the worst answer, and those are in between, okay? Right. So, what are the pros of using reinforcement learning to do fine-tuning? The first thing is that reinforcement learning is useful whenever the objective is hard to formulate mathematically, which is typically the case here. Because if you're talking with ChatGPT and ChatGPT, you ask something like, what is Washington, D.C.? And the model outputs something like, Washington, D.C. is the capital of Venezuela. Well, the first part is good, the last part is very wrong, so you would like to tell the model that this is a wrong answer. But how do you formulate mathematically that concept? That's something that is going to be very hard. On the other hand, if you can just interact with the model and tell it, oh, wait a minute, this was very wrong. Instead, let's look at, it is the capital of the United States of America. Then, you can basically say when it was right and when it was wrong. The other thing is that reinforcement learning is versatile in the sense that the framework I've shown at the beginning with the environment and the agent, etc., of course, it works with large language models, but it works also with anything else. It's completely oblivious to the modality that you're treating. The other thing is that it has been shown that reinforcement learning works pretty well for continuous improvement. So every time you have a little bit more data and you add this data to your data set to do a little bit more fine tuning, your model will get better and better, which is not necessarily the case with supervised learning. And it's computationally efficient. For some reasons that we can talk about later, reinforcement learning requires, let's say, less backpropagation or less backpropagation than using supervised learning models. Right, there are also problems with reinforcement learning. The first one is that reinforcement learning is less obvious than other methods. It requires a lot of technical knowledge and these kind of things, but thankfully we're there to help. And another thing is that reinforcement learning is an incomplete patch. So if I take the example of the model outputting the wrong country for a certain capital, you can patch that once, but that does not mean that it's going to learn all the other capitals from all the other countries, right? So you're going to need to do like patches one at a time, sort of. And that's obviously not ideal because you're not improving really the logic of the model itself. You're just like saying, oh, this is wrong. Try to do better there. Try to do better there. But you're not making the model better like in itself. And another problem is that the training of reinforcement learning so far is mostly centralized in the sense that you need to collect data from all the users and then retrain the model as a whole. And so far, we have not really figured out how to do fine-tuning of using reinforcement learning on device, which I think would be really nice. If we could do fine-tuning of each and every person's version of ChatGPT on a device, that would be really awesome. Right, so RLHF step by step. We need three things to do reinforcement learning from human feedback. The first one is obviously a generative model, something like a GPT model or whatever generative model you have. And then you need some extra data. This extra data is basically the data label that we talked about, either using ranking or accept reject or something like that. So you basically need to have actual people looking at the data and saying this was a good answer, this was a bad answer. The best scenario is obviously when the data is paired or at least put in batches. You have one question and multiple answers and you can rank those answers or just put a label on them. It's much harder if you have an imbalanced data set or this kind of things. And you need a reward model. So basically the reward model is going to be a model that looks pretty much like our generative model, but instead of generating data, it's just going to put a certain scalar value based on the output of the model. And I'm going to come back a little bit later about on what the reward model precisely is. So you have three phases in the training. First, you train your generative model on a static data set, Wikipedia or something like that. Next, you train your reward model to basically accurately predict what is a good answer and what is a bad answer. And then you combine the two. So your model that you have trained in the first phase, the reward model, you put the two of them together and you retrain your model basically to maximize the reward function using an algorithm that we call in reinforcement learning PPO for proximal policy optimization. It's not very important, but that's basically one of the basic building blocks that you need. So the key terms in all of this is the reward model and PPO. So the reward model, to give you a little bit more insight about what it looks like, imagine that you have your GPT model with all these layers. And what you could do, and what some people do, is that they just take the last layer out, they replace that by a simple linear layer that outputs a scalar value. And now you're going to retrain that model based on the ranked data to output a positive value if the data is good and a negative value if the data is bad. And you train that model for a little while, and then you get that reward model that is basically capable of giving a certain measure of quality of the output of the model. Then you freeze that model, and you use that model during the reinforcement learning phase as basically a tool to judge on the quality of the output. And you train the first model that you had, so GPT, to basically say, okay, let's try to maximize the reward, and to give answers that give a very good reward. So there are obviously already some open source solutions out there to do reinforcement learning from human feedback. and our goal is not at all to replace them. If you look at those solutions, you most of the time have a single high-level entry point. So you have something like a trainer class where you can put your data and you can put a model, and then it's going to do everything for you. So that's very handy if the problem fits the prerequisites. So if you have a data set that fits those prerequisites and a model that fits those prerequisites, something like, okay, everything comes from Hugging Face, and I know that I can plug those things in very easily, that's great. Go for that, like it's going to work out of the box, and that's awesome. But if you have a new problem with a data set that does not really fit, or a model that is a little bit more special, or maybe a modality that is not covered, or something multimodal, all these kind of edge cases that maybe were not predicted at first, then you're going to have a problem with those high-level entry points. So it's not ideal for research and development. So what we propose with TorchRL is basically a solution where we have low-level primitives for other maintainers to use. So basically, if you want maintainer of those high-level libraries, our goal is basically to make your life easier, to reuse those components and make things a little bit more flexible for the user such that they can apply that to their problem. We want to build an ecosystem where experimenting is easy. So we want also that if people want to switch one dataset with the other, and maybe the datasets are presented in a different way, that shouldn't be too much of a problem. Same thing if the model is different. Same thing if you have a multimodal model or a unimodal model and you want to swap them. All these kind of cases, we want to cover them. And we want also to build coding standards within the RLHF community such that we can move faster. Because I think that if all the people that are working in the field talk sort of the same language, and we know that we have those basic building blocks, and we can identify what they are, and we can swap them easily, it's going to be much easier to progress fast within the field. Cool. And so what we have is a bunch of tools to do better data formatting, and also we're having better training standards. So what is TorchRL? So TorchRL is a library that we open sourced about 2 years ago, and the goal is to keep PyTorch at the forefront of RL research and applications. What we provide is a set of low-level abstractions to do reinforcement learning. We want to unify all the reinforcement learning backends and solutions. So if you look at the reinforcement learning ecosystem, it's very fragmented. You have a lot of simulators like GIM or DeepMind Suite and all these kind of things. It's sometimes very hard, to swap those components one with the other. And so what we want within TorchRL is to provide something where we cover the whole space and where it's very easy to implement new solutions. We focus a lot on modularity. So something you've heard me already talk about quite a lot is that we want to be able to swap components. So we talked about, for instance, of PPO, which is one specific reinforcement learning algorithm. In most of the trainer class that you see in RLHF, people stick to PPO and they don't even consider changing PPO with something else. In TorchRL, swapping PPO with another algorithm is very easy because all of these things are a different class and you just need to swap one class with the other and it's going to work out of the box. We focus a lot on breadth rather than depth. Our goal is really that it's easy for people who use the library to develop their own solutions. We don't want to dig too deep, but we want to make sure that we cover every single part of reinforcement learning. And it's easy to hack. So we document our classes well, not only regarding usage, but also we document a lot how to change a class, how to inherit from a class and create a new one, etc., etc. And we focus obviously a lot also on efficiency regarding speed of data collection, distributed training, model ensembling, and all these kind of things. This is what the training loop looks like in TorchRL. So what you see on the left is basically on the top left, what you have is the data collection loop. So you have an environment. So remember the environment in our case is something like a user interacting with ChatGPT. You have an actor. The actor is ChatGPT itself, outputting answers. And then you have this loop, of the conversation, basically. The user asks something, ChatGPT answers something, and then you ask something else, and you go back and forth like that, and you build sort of a mini data set that you're going to give to your loss function later on. Right, so we pack all the data together. We put that in a replay buffer, so that's basically our data set, but it's evolving throughout the training process. And then we sample something from the replay buffer, feed that to the loss function, adapt our model a little bit, and then go back and collect some new data to train the model. Good. So the problem in reinforcement learning that we identified with TorchRL is that it's something, as we said before, that is very versatile. So it covers a lot of modalities. And it's not easy to build those classes while keeping in mind all the things that you want to put within the data set. Because it could be images, it could be state vectors, for physical robots. It could be financial data. It can be basically anything, or text in this case. So what we came up with is a tool to do better data representation. And that's basically at the very core of what TorchRL is. So this data representation tool is called TensorDict. So TensorDict is a dictionary-like and a tensor-like class. And it supports many tensor operations. Like, for instance, you can stack TensorDict together. You can put them on a certain device. You can move them from a device to disk. You can do distributed point-to-point communication with two TensorDicts situated on two different nodes and all these kind of things. It's the key data structure that really powers TorchRL. So if you want to use TorchRL and you just want to use one class, the only thing that you need to buy is TensorDict most of the time. And we use TensorDict within RLHF in 3 different modalities. The first one is for data representation. So we can, as I've said, move things from one device to the other or from disk to device. In RLHF, it's also used to represent data in a convenient way, in the sense that what you're going to have is, for instance, this dictionary or even a data class, because TensorDict also supports a data class-like format, where you say, okay, this is the reward, this is the prompt, this is the output, etc., and it keeps the data very well organized. And that basically allows you, if you want to reuse your script across different modalities, for instance, to keep things organized in the same way and not polluting your code with things like, oh, well, if this is a training loop that treats images, do that, and if it's text, do this, because TensorDict abstracts away all of these things within the data structure. The other thing that you can use TensorDict for is parameter serialization, which is very useful in RLHF because we manipulate a lot the model. I took the example of the reward model where we substitute one layer with another. Well, you're going to do the same, across the training loop, and freeze parts of your network and all these kind of things. So manipulating parameters is very important in RLHF, but also very difficult. And with TensorDict, when you represent your parameters are represented in the exact same way as your model. So if you know what a state dict is in PyTorch, it's basically something that is completely flat. You take your model, which is highly nested, you have the first module within the second module, etc. And this highly nested structure is completely flattened when you represent a state dict. And that's not very handy, right? Because if you want to access just one set of parameters, you cannot really disentangle it from the rest. With TensorDict, it's completely different because TensorDict is represented exactly like your model is. And also it's very easy to freeze part of your network and specifically say, okay, I just want to take those parameters, freeze them, or on the contrary, make them trainable and similar things. It's also very easy to serialize the parameters on disk, to move them from a specific disk location to a QD device, or to basically synchronize the parameters across workers. And finally, TensorDict is used also for model execution, so it's packed with a certain number of classes that we call TensorDict module that allow you to programmatically build a model. And again, because we want to manipulate the model in RLHF, it's something that comes in very, very handy. The final part is fine-tuning with RLHF. So what we propose within TorchRL is first a Hugging Face model interface. So we give you the tools to represent a model from Hugging Face as a reinforcement learning model. Again, it's not something that is very easy to do because your model acts a little bit differently in reinforcement learning, because there is all this concept of reward and making actions. People don't usually call that actions, in supervised learning. So there is a lot of interfacing that needs to happen, and we take care of that. And also the data representation. We also provide a lot of losses, so typically PPO that everyone uses in RLHF, but also other things if people want to experiment with other losses. And finally, we propose a lot of classes to do the RLHF tricks, things like KL reward and all these kind of things that basically prevent your model from diverging too much from its initial configuration after the initial training phase. Okay, so to wrap it up, RLHF is an active area of research, and we want to promote that. We want for people to easily experiment in RLHF. And what TorchRL wants to do is basically to build common research standards within the RLHF community, and also give efficient tools for people to quickly hack, quickly experiment, and quickly develop the tools of tomorrow. Thanks for your attention, and that's it for my talk.
Please join me here for the Q&A. We also have some questions, some interesting questions. So first one, how do you recommend to train people to rank or evaluate generated text in an objective way? It's not so much about maybe the framework.
So I took the example of saying, well, you interact with ChatGPT and you have the thumb up, thumb down, and you can rank data with that. I'm not entirely sure OpenAI really uses that to rank their model because, as the question points out, you're not really sure of what's going on, and you expose yourself to have people hacking their way through, trying to fine-tune the model for a specific nasty goal. So what they do instead is that they have people working for them, things like Amazon Turk and these kind of things, where people are basically paid to read the answers and rank them, and so what happens most of the time is that people identify a faulty answer within ChatGPT, they report that, and then the company is gonna put people on that, ask the question, ask different versions of that question, do the ranking, and retrain the model. So it's not actually you who's giving feedback, but it's someone else.
Okay. There's another question that is voted. Public human feedback is likely to be at least somewhat noisy, and maybe you already answered a bit this. One person would consider acceptable or good. So that's basically what you just said. You don't actually use directly, but somehow. There is another question here that I think it's in the last months, supervised fine-tuning of LLMs has been commoditized, with everyone releasing their own fine-tuned version of the base models. Oh, this is moving. Where is it? The same can be said of RLHF. Supposedly, it seems to be mostly done by main players in the field. What are your thoughts on that? Why isn't RLHF done by most of the companies?
All right. I think one problem might be that it's not necessarily easy to come up with something that works. And again, that's why we're here. That's something I see at work, when interacting with people, when you tell them, oh, let's use RL to solve that problem, usually there's a little bit of, oh gosh, really? Yes. And so I think that's where we come into play. That's what we want to do, is to make that process easy, to build the interface for people to say, okay, I'm not afraid of RL anymore because I know there are people covering for me. And that's also why I think that those high-level libraries are great, but you need to trust them a lot. Yeah. And I think that trust also comes with a lot of people from being able to hack through the code and understand what's going on. And that's what we try to do, to have something that is a little bit more low-level, maybe for other people that do high-level to use, and make things more transparent.